Hey you guys, this is Steve Yang,
Dang Tongue.
And Ariana.
And Mrs. Kato.
and we'll be having a great time talking about the history of the atom. And it is about Chapter 4, pages 101 to 109, and Chapter 5, pages 127 to 129.
History. The Greek philosopher Demo something from 460 BC to 370 BC. So yeah, that guy.
He's pretty handsome.
Oh yeah, of course.
He looks like Will Ferrell, doesn't he? With the beard.
Amazing.
Sure. He coined the term atomos. He believed atoms were indivisible and indestructible.
Okay, let's move on.
So Dalton's atomic theory states that all elements are composed of tiny indivisible particles called atoms, and this happened in the 1600s, and then atoms of the same elements are identical. Elements combine in simple whole number ratios to form compounds, and that elements are never changed into atoms of another element as a result of a chemical reaction.
So which one of these are true?
So we know that number one is definitely false, because we can actually divide atoms into protons, neutrons, and electrons.
Right.
Number two is also false, since we could have ions and isotopes, which makes same element atoms unidentical. Number three is correct. And number four is also correct, unless it's a nuclear reaction.
Yay.
Yay! Nuclear reaction. Okay, moving on.
History. Thomson discovers the electron.
Yay!
And he used the-
Excited for electrons.
Yes.
And he used a cathode ray tube.
And this is what a cathode ray tube looks like, and you put high voltage electricity through it, and the electrons in the atom get excited, and then there is a beam. With a positive plate on one side and a negative plate on another, you can see that the beam is attracted to the positive plate, now indicating that the beam is made out of something that is negative, and that something is the electron. So televisions used to be called a tube. You watch the tube. And the reason why they were called the tube was because inside these bulky televisions and computer monitors are cathode ray tubes. You can research that more if you want to know more about it. Then came Millikan, and Millikan determines the mass to charge ratio of the electron. So if you look through history, it may be a little bit confusing because Thomson and Millikan came around the same time, and with each other's help, they were able to find the mass of the electron, and that came out to be about that much. By the way, this number, you don't have to memorize. You may need this number in physics, but you will not need it in chemistry. So with Thomson and Millikan's research, they all knew that if there were negatively charged electrons, there were also positively charged protons. And so Eugene Goldstein came along and he confirms the existence of a proton. And he measures the mass of the proton and finds out that it was 1840 times that of an electron, which we call 1 AMU. And by definition, 1 AMU is 1/12 of carbon 12. So we knew that carbon 12 has 12 protons. Sorry, not 12. 6 protons and 6 neutrons. And considering that we know this already, they arbitrarily came up with this one SI unit, and this SI unit is 1 AMU, and they said this 1 AMU is equal to 1/12 of a carbon 12. Then came, but they realized, oh wait, this proton and this electrons should weigh 6 AMU, but it doesn't. It weighs 12 AMU. And so they came up. They knew that neutrons existed, and then Chadwick came along and confirmed the existence of a neutron. So at this point, they all knew that there were protons in an atom, there were electrons in an atom, and they also knew that there were neutrons in an atom. And according to Thomson, he believed that these neutrons and protons were kind of scattered, kind of like a blueberry muffin. You know that blueberries are kind of all around inside the muffin, and likewise, people believe that protons, electrons, and neutrons were kind of spread around the entire atom evenly. And this we call the plum pudding model. And then came Rutherford. And Rutherford does this experiment called the gold foil experiment. He gets an alpha particle, and we're going to find out what the alpha particle is, and we're going to become very familiar with it in just a little bit. But he shoots these alpha particles onto this very thin gold foil, and he expects, assuming the plum pudding model of the atom, he expects that most of this alpha particle will go straight through and hit the sensor in the opposite side. And it did. For the majority of the alpha particle did go straight through. However, very few scattered all around this sensor, and some of them came straight back to the opposite side. And so he observed that most particles passed through. He also assumed that few particles were deflected, and then even fewer greatly deflected. And so he thought, oh, the alpha particles must have hit something. And so here came his conclusions. So most particles passed straight through, meaning that the something that he hit must be very, very small. He saw that few deflected, meaning that the nucleus, whatever that thing that the alpha particles hit, must be very, very dense. So it's very hard and dense and not movable thing. And he also saw that very few greatly deflected, meaning that it must be a positively charged nucleus, because the alpha particles were positively charged, so it must have hit something very positive so that it does not stick, but it actually bounces back. And so he concluded that in the atom there is a nucleus. And the nucleus is small, dense, and positively charged. And so going back to the drawing, so here's alpha particles coming from the left to the right, and majority of them go straight through because the nucleus is small, and some deflects because the nucleus is not movable. It's a very hard, dense material, and it is positively charged, meaning that the alpha particles, the alpha particles are positively charged. It bounces back. It does not stick to the nucleus. And so now we know that electrons have a negatively 1 charge, and protons are positively 1 charge. Neutrons are no charge. Electrons have a very small mass, which is 1/1840 AMU. However, we're going to consider that about 0 AMU. Protons are also 1 AMU. Neutrons are 1 AMU. In mass, it's 9. Let's see. Erase that. In mass, it is this mass here. Oh no. And we don't really have to be very familiar with this mass numbers here, unless we're doing the mass defect calculation, and I'll give you that number in a little bit when we need it. We also know that electrons are in the electron cloud. However, the rest of the atom, protons and neutrons, which are the heavier particles, are in the nucleus. So about 99.99% of the mass of the nucleus the mass of the atom is inside the nucleus. And then came Niels Bohr's model, and his tests showed that electrons are at fixed distances from the nucleus, and they move in a circular orbit. So the key word is orbit, not orbital. And so kind of like the Earth orbits the sun, these electrons are orbiting the nucleus in this theory. This is a theory of the atom that you guys may have learned about in junior high, and we're going to use this to a degree, but mostly we're going to use the quantum mechanical model of the atom, and we're going to go into that further in chapter 5. And so Dalton's atom was a big mass of spherical mass. And then came the plum pudding model with the protons and the electrons kind of like spread out like a blueberry is in a blueberry muffin. And then came Rutherford with a nucleus in the middle with the electrons spread around, and Bohr's model with the nucleus in the middle and the electrons orbiting the nucleus. And then here is our current orbital atom model here, and we're going to go through that with chapter 5. And that concludes our first podcast of Unit 4. Thanks guys for watching.